Hi, this is Seth, and in this video, I'm going to show you how to make R do your algebra homework. Now, right off the bat, I'm going to say that if I needed to solve an algebra problem that I couldn't just solve in my head, R is not the first tool that I would turn to. I'd probably turn to MathPapa or WolframAlpha or probably Desmos, and those will be making some appearances here shortly. But why would I make a video on this topic? For three reasons. First, R is a language like any other language. And just like you might not, suppose you're learning Spanish and you think, oh, I don't know if I really need to know the names of these obscure plants in Spanish. You're probably right, but learning the names of those plants in Spanish will make you more fluent in the language. And that's what this video is all about. This is something that is within R's capability. And if you want to increase your fluency in the language, you can learn it. Second reason, this will prepare you for any coding scenarios where algebra may become relevant. Kind of like if we carry the analogy forward, if you did find yourself in a conversation in Spanish talking about obscure plants, you would be ready for it. And then third, some of the functions I'm going to show you, or really specifically the solve function, you're going to see that again, especially if you get into more advanced math like matrix algebra. So let's go ahead and just jump right into it. We can use R to solve simple linear equations. There's a few different ways we can do this. So our first problem, we're solving for x in this equation. 2x plus 3 equals 7. Now the answer is going to be 2, because if we double something and add 3 to get 7, the only thing that's going to give us that is 2. So one way that we can solve this is by just rearranging the formula. Now, so you might immediately have the thought, can I do something like 2 times x plus 3 equals 7? Let's see what happens. It says no. And what the problem here is that equals in this case is referring to an assignment. In R, the primary way you want to think about the equal sign is as assigning something. So, for example, if we said Seth equals 1 through 5, we run that. If we say, print Seth, what is Seth? It's going to say 1, 2, 3, 4, 5, because we've assigned Seth to mean that. So the equal sign is serving not exactly the same kind of function as you might typically be thinking. So it's not going to be as intuitive as something like MathPapa. So I'm actually just going to jump over here real quick and let's just see. If we wanted to solve this in MathPapa, we could say 2x plus 3 equals 7, and it spits out 2. So if I were solving this kind of problem and I didn't want to do it mentally, something like MathPapa is the first thing that's going to pop into my head. Or WolframAlpha, it can do this. WolframAlpha is more advanced than MathPapa. It can do calculus and other fun things. Here we go, the solutions too. But what I like about MathPapa is it displays fractions in a way that I really like. It displays fractions in ways that the way I would write them if I were writing them on a sheet of paper. So I really do like MathPapa for certain kinds of things. Even if WolframAlpha is more powerful, that same thing would have to be represented in this less intuitive way. Anyway, we could also solve it in Desmos. We could say 2x plus 3 equals 7. That describes this line, which intersects the x-axis as at 2. So all three of these ways are way faster. But again, we're trying to build some fluency in R, or at least that's how I'm justifying the fact that I decided to make this video. So one way we can do this is we can rearrange the formula. We could say, all right, let's subtract 3 from both sides and divide both sides by 2, because we're trying to isolate that x. So we could say x is equal to 7 minus 3, and we're putting this in parentheses and dividing by 2, because we've subtracted 3 from both sides, divided both sides by 2. That's what gets the x all alone. then, as I often do, I'm going to say semicolon and then x, because what this means is I'm saying do this assignment, say x is equal to 4 divided by 2, then tell me what x is. That's what this line of code says. So when we run it, we get 2, which is what we knew we were going to get from the other ways that we solved it. Okay, so that's one way. It came out to 2. We can also use this function that I mentioned earlier, which is solve. This one's pretty cool. Solve takes, we'll focus on, think of it as taking 2 arguments. The first argument is your coefficients, or coefficient if there's only one. The second argument is your constant part. So the coefficient in this equation, the coefficient is 2. It's the value we're multiplying times this unknown variable. The constant is kind of the rest of it, the part that's not attached to anything else. So the constant here is 4, or 7 minus 3, because that's the part that's not being multiplied times our variable. So if we plug in the coefficient and then the constant, we'd say solve. Our coefficient is 2. You can see that right there. That's what's being multiplied times x. Our constant is 4, or if you like, you could just say 7 minus 3. Maybe you're working on the kind of equation that's more complicated and more of a pain to do in your head, so you just say 7 minus 3 without actually working through it. What do we get? 2. I'll give us a little bit more space down here. So when we use solve and then enter 2 as the coefficient, 7 minus 3 is the constant, we get 2. So once again, one more way of showing that if we solve for x, we're going to get 2. Now, if you're like me, you really like the appeal of something like MathPapa or WolframAlpha, where you just kind of throw it in there and it knows what you want and it solves for x. We can make that happen, but we have to do it in kind of a wonky way. So our third way of doing this is using yakas, or specifically R yakas. This is the most current version, I guess. I like to use an older version, so R yakas 0, because I like how it works. I guess I could learn this one, but once again, I'm probably not going to be. I'm showing you how to do this to show you it's possible, but this is not how I would be solving it myself. So let's say, first of all, if you don't have this library, you need to say install.packages and then install the package in this case. So it'd be R yakas 0. I've already installed it, so I'm just going to call it up with library, open parentheses, R yakas 0. Okay, now here's the format. What we say is yakas, which means we're telling R to go consult this other platform, this other tool, and then we use this this argument. We put it as a string. We put it in quotation marks. We say solve. We put the equation, comma, x. All right, let's see what that would look like. We'll say yakas, open quote, solve. I believe it does have to be capitalized, open parentheses. And our equation, what's it trying to tell me? Oh, don't worry about it. Our equation is 2x plus 3 minus 7. Okay, so we'll say 2 times, remember we need to use an asterisk in R to indicate times, 2 times x plus 3 equals 7. And I'm putting 2 equal signs, which is really indicative of the fact that we're not assigning anything. We're literally saying it is equal to 2 times something, then add 3 is equal to 7. Okay, then am I doing that wrong? Yeah, so we've got our equation, then we say comma, then x, because we're saying, hey, by the way, solve for x, close the parentheses, end quote, end parentheses. I think this should give us 2. Yes, so it gives us x is equal to 2. So we get the same answer. Now, I mean, I guess if you really, really want to just be able to input it without having to rearrange, it works, but that is kind of a mild pain to get through. But anyway, there it is. If you want it, there it is. Let's do another real quick. We're solving for x in x minus 2x plus 33 equals 3. This one looks like kind of a pain to rearrange. Like if we wanted to use solve, we'd have to think, okay, after we subtract 2x, we'll end up with a -1 coefficient. And then we subtract 33 from both sides, we end up with a -30 coefficient. So this would work. You see, we get 30 is the answer. We could do it that way. But just because there's kind of a lot of mental gymnastics to go through there, this is one where I would probably use Yakka's. So we'll say solve x minus 2 times x plus 33 equals 3. And then comma. The next argument is what we're going to solve for, which is x. Okay. Close parentheses, close quote, close parentheses. Boom. It also comes to 30. Not 309, 30. Okay, so we've solved 2 algebra problems. And it is not lost on me how much faster it would be to simply plug these in to get 30 with a tool like this. But we're going for completion here, right? We're going for as much understanding of how R works as possible. Okay, here's sort of a variation. Third problem. If x is 5 and y is 3, we could solve for z in this equation. Z is equal to x squared plus 3y minus 7. Well, one way we could do this is we could just say, okay, x is 5. Okay, whoops. And then we'll say y is 3. It's equal to 3. Y gets 3, as we often would say. And then we can just solve. We can say, okay, so z is equal to x squared. That's how we indicate it squared, up caret 2, plus 3 times y minus 7. Okay, and then if we have it run that operation and then tell us what z is, we get 27, which, well, 25 plus 9 minus 7. Yeah, that's going to be 27. So that's correct. This is just to show how R can take this information, and it's just thinking, oh, 5, x means 5 in this case, and y means 3, so 25 plus 9 minus 7, and it comes to 27. Okay, so we've solved some simple linear equations. Let's take it up a notch. This is the part a lot of people hate, which is systems of linear equations. Now here we can use our solve friend again, but what we're going to do now is, in this case, when we have a system of linear equations like here, 2x plus 3y equals 8 and 3x minus 4y equals -11, now we've got 4 coefficients and 2 constants. So what we have to do, the solve function is still going to work, but we're going to have to put in all of these coefficients and all of these constants. So we'll put in the coefficients as a matrix, which it's a 2-dimensional way of representing data. Don't stress about what that means right now. And then we'll input the constants as a vector. A vector is a 1-dimensional way, or just like a row of numbers or a set of numbers in a row. Now, typically, if I were going to solve this, I love solving this kind of thing in Desmos, just because I really like seeing. So 2x plus 3y equals 8. That's our first line. 3x minus 4y equals -11. That's our other line. Our answer should be -0.05882 and 2.70588. That's the point where these two lines intersect. And that's what it means to solve a system of linear equations. What we're saying is, what would be the coordinates for x and y that would satisfy both of these equations? And because these are straight lines, there's only going to be one, which is right here, because they're intersecting. Okay, so we know kind of what we should be getting. Let's figure out how to make R calculate that. So we'll use solve, we'll input our coefficients as a matrix, and then our constants as a vector. So here is, so first I'm just going to create something called A. I'm going to assign A, and it's going to be a matrix. So whenever I enter A, it's going to refer to a matrix, which is 2 dimensions. Think of like If you have an Excel spreadsheet and you're seeing columns and rows, that's a matrix. It's a two-dimensional array of data. So create a matrix. Okay, it's going to be a combination of things. So we're going to give it a list of things to include. Our aficionados will be annoyed that I use the term list, but I don't allow comments, so there's nothing they can do about it. So what are the pieces? We're going to put them in this order. We're going to say x1, then x2, y1, and then y2. Okay, and then the number of rows is equal to the number of equations. All right, so just step by step, we're going to say x1, x2, y1, y2, and the number of equations is 2. Okay, so let's just look at it. We've got 2, 3, 3, -4. Don't forget the sign of the coefficient. All right, and because it is two-dimensional, R needs to know how many rows we're talking about. So in row, number of rows is 2. Okay, so let's just run that and see what we get. We get a 2D array of data, the 2, the 3, the 3, and the -4. The same thing here. We've taken our coefficients and put them into a matrix. All right, next we do the same thing, but it's even easier because we're just going to put these constants, 8 and -11. Remember, the constants are the parts that aren't multiplied times the variables. They're just sitting around on their own. They're constant. We're just going to enter them. We're going to call them B. We called our matrix A, so we're going to call this B. So B is equal to a combination of things, specifically 8 and -11. So here's the format. B is equal to C for a combination or concatenate or whichever term you like, and then put in your first and second constants. All right, so let's see what that looks like. When we run it, we've just got a vector, which is, whereas a matrix is in 2 dimensions, we've got vertical and horizontal. This is just in a single row or a single column. It's actually arbitrary whether you think of this as a column or a row. But anyway, you can see B means 8 and -11. So next we just solve it. A means what? A means this matrix of coefficients. B means these constants. What does the solve formula want? This function, it wants to get the coefficients, then it wants to get the constants. Let's see what we get. Oh, those are the numbers I was hoping to see. Let's just double check again real quick. We should be getting -0.05882 and 2.70588. Yeah, so we got exactly the correct answers. Now we can take it up a notch. We can solve a system of 3 linear equations. So here I've got 3 different equations. I'm going to do it faster this time, but I'm going to use the same procedure. So A is equal to a matrix of a combination of things, 2, -3, -2, 1, -1, 1, -1, 2, 2. So that was 2, -3, -2, 1, -1, 1, -1, 2, 2. That's where that's coming from. And as a reminder, we're now going to say number of rows equals 3. Okay, so let's see what we get here. Yep, we've got all of those coefficients now expressed in a 2-dimensional fashion. And then to get our constants, we'll just say B is a combination of things. It's 8, -11, -3. Let's see what we get. 8, -11, -3. Solve for A and B, and we get, we get 2, 3, -1. So there you go. 2, 3, and -1. Now we're in 3 dimensions, which is why there are 3 coordinates. We've got X, Y, and Z. Okay. So there you go. Systems of linear equations. What fun. Am I right? Now let's go on. I'll cover one more topic, which is quadratic equations. Now, when we're looking for a quadratic, when solving a quadratic equation, we're typically trying to find the roots. If we're solving for X, we're trying to figure out where the equation intersects the X-axis. We can use the poly root, so polynomial roots. That's what that means, polyroot function. Somewhat obnoxiously, though, we're going to have to enter the coefficients in the opposite order than we would naturally think of it. So you probably, if you know much about polynomials or quadratic, you probably think of it in some sort of form such as ax squared plus bx plus c. We often like to put our exponents first. Well, for polyroot, you're going to do it backwards. If our equation were ax squared plus bx plus c, we would use polyroot, open parentheses, c, b, a, putting in the coefficients backwards from what we're used to doing. So let's just visualize real quick what's going on. We'll deal with 3. We'll say x squared minus 2x minus 1. So here the roots of this parabola are 2.41 and negative 0.41. So that's a quadratic equation with 2 roots. We can also have a quadratic equation with only 1 root, so it's only intersecting the y or the x-axis at 1 point. So x squared minus 2x plus 1. So you can see it's just tapping that x at one place. The root is 1. Then we could also have a quadratic equation where it's not intersecting the y or the x-axis at all. So here, what am I doing? Oh, sorry. That was the same one I just had. Okay, so here you can see it's not intersecting the x-axis at all. So it does have roots, but they're imaginary roots. So we're dealing with complex roots. So 0 real roots. So yeah, let's just go through. We know sort of where we're expecting these values to shake out, but let's just check and see how we would do this. Okay, so first we've got x squared minus 2x minus 1. We can use our polyroot function. Remember, it's got to go, if it was a squared plus bx plus c, it's got to go cba. So we're going to say negative 1 is our first coefficient, negative 2 is our second, and 1 is the last one. Because we've got negative 1, negative 2, and there's just an invisible positive 1 right there. All right, what do we get? What am I doing? Does polyroot want... Yeah. Okay, so I forgot how the function works apparently. So for polyroot, we need to, I was just trying to cram the coefficients in there, but what it wants is we need to enter them as a combination. So the first argument is the coefficients, and you can kind of think of as a combination as sort of like a list or a vector of things, and they are negative 1, negative 2, and 1. So now whenever I do that, it gives us negative 0.41 and 2.41, and we're hoping to see that. We've got negative 0.41 and 2.41, so it's giving us what we want. The next one, as a reminder, it intersects at 1, so we're hoping to get a root of 1. I'll do it correctly this time. Polyroot. C for a combination of things. Now, let's see, we've got x squared minus 2x plus 1. So 1 is our first coefficient, negative 2 is next, and then 1 is the last one. We just get 1. It spits it out twice, which is sort of annoying. Oh, and you might even notice it's giving us the answer in complex terms. So because we've got real roots so far, it's giving us the imaginary part multiplied times 0. So this comes out to 2.41 plus 0 times I is the same thing as just 2.41. So here we're just getting 1. And it's spitting it out twice because it just can't, I guess it just can't understand that that's a single root. Okay, let's do one more. As promised, I said we'd do this one where we've got, so now that complex form is going to come in handy because we're going to have complex roots. So let's find out what it is. We can use polyroot, open parentheses, a combination of things, and we're going to say 2, negative 2, and 1. 2, negative 2, 1. and we get 1 plus I, 1 minus I. And that's correct. That's what the roots are. So you can see we've got, we're adding, here we've got complex numbers, and so that's what's represented here. The real part and then the imaginary part. Okay, now that's sort of everything that I had wanted to cover. So at this point, you could say, cool, I'm done, so long. Or maybe you said that long ago and you're not here anymore and I'm just talking to myself. That could happen. But in case you are still here and you're like me, maybe like me, you're sort of annoyed by seeing it give us multiple roots when there's really only one root. Or maybe you don't want to see this 0i. So we can actually write a function that solves a quadratic equation without including those parts. And if you wanted to, here's one way you could do it. I'm sure there's a more efficient way to do this, but here's the code that I used. I created a function called quadratic. Quadratic is a function. It takes arguments a, b, and c. So I'm going to take those coefficients in the typical order. What this part does is it makes it so that it's capable of handling complex values, which is what we're often going to want. This is calculating the positive root. This is calculating the negative root. This is, by the way, this is just the quadratic formula. So if that looks kind of familiar, that's where it's from. Then this line is saying these lines, if there are no imaginary numbers, then treat these as real numbers. So kick the I part unless there's an imaginary part to it. And then this part says if the roots are the same, just treat them as 1. And then just spit it out. So we're going to enter our coefficients and it's going to spit out what we want. So let's work through these again. We've got, I better run this so that it exists. Okay, so now that this function means that, I can say quadratic, and then I'll enter in this equation 1, -2, -1, and what do we get? We get those answers we're looking for, 2.41 and -0.41. Quick reminder, that's those were the roots, -0.41, 2.41. And notice I've got it set up so it's not showing us that I, the imaginary component, anymore. Here, problem 7, which is this line, it's intersecting just at 1. We can use quadratic. First argument is 1, second is -2, third is 1. What do we get? Should just get 1, and we do. So it doesn't repeat itself. It doesn't include the imaginary component. And then lastly, here we do need the imaginary part because this is not landing just on the real number line. It's rotating into imaginary land. So we can say quadratic, 1 is our first coefficient, -2 is the second, +2 is the third, and you can see those right here. So we should get, 1 plus I and 1 minus I. Now I want to adjust the function so that it excludes this 1 whenever this happens, because I just wanted to say 1 plus I, 1 minus I, but that sounds like more work than it's probably worth. Okay, and then as a quick reminder, we can still use yakas to solve this. So which one are we solving? Let's say, we're solving something like x squared minus 2x plus 2 equals 0. Solve for x. If we use this, it gives us the answer in imaginary terms. So it says it's giving us something complex. So the first value is 1 plus I. So the second value is in the second dimension. So that's up 1 is I. And then 1, -1. So let me just make this parallel because this might be confusing to look at. We're going to be dealing with what? 1, -2, 2. This is the equivalent of 1 plus I, 1 minus I. Yeah. This is how it represents it. The I value is represented as a second coordinate. And so here it's negative I, here it's positive I. But this is a little bit confusing to look at, in my opinion. And also, if at this point we're basically telling R to go ask some other mathematical tool to solve the problem and then come back to us. So at some point it's like, just go use the other tool. You know what I mean? But anyway, this exists if you want it. Okay, that's probably more than you ever wanted to know about how to apply R to solve algebra problems. Next time, I think I'm going to show you how to use R to solve trigonometry problems, which I think is actually pretty fun. And I actually do use R to solve trig problems periodically. All right, that's it. Have fun. Happy coding. Happy algebra. See you next time.